Hello everyone, thank you for having me. I'm Louis. I'm working as lead cryptographer at Holonym Foundation, building human tech. And my talk for today will be about cryptography and how we build human network and how we applied it to specific use cases, which is quite related to the previous presentation from AJ on biometric authentication. So first of all, I will quickly present to you our network, human network, how we build human keys, and this AVS and how all of the nodes are operating together to do some multi-party computation, and how this could be used then for one approach of biometric authentication. So first of all, one of our main ideas at Human Tech was to being able to, so we introduced this concept of human keys. So human keys are cryptographic keys that are being derived and generated from human attributes. So what is in human attributes could be anything that you are, that you have, or that you know. And this private input from the user could then be secured by some kind of function as masking, and then send away to a network, our human network, which is an AVS, and to be able to perform computation on this private input and to retrieve cryptographic keys back to the user. So what's an AVS? An AVS stands for Autonomous Verifiable Service. It has been introduced by EigenLayer a couple of years ago. It is a type of network where operators are running nodes, and they benefit from the economic security of risk-taking. So risk-taking is a bit similarly as staking, but just like in the fact that one delegator can allocate funds and delegate to multiple operators and can actually secure multiple AVSs at the same time. So our human network is an AVS live on EigenLayer, symbiotic. So it's what we offer here is multi-party computation, and it's a decentralized threshold network. So what does that mean? It means that we have a set of nodes, and n of these nodes are sharing a secret. The secret is the network secret. And it is called threshold because in a T out of n setup, that means that you only need T of these n nodes to come together and perform the computation to actually perform the computations that you want. So that's why it's T out of n. N nodes are sharing the secret, but you need only T of them to perform the computation. And this secret, the network secret, is shared among all of the nodes, all of the n nodes, and every day for security reasons, we are performing a resharing process. That means that the secret is then re-shared, re-divided, and shared among n new nodes that are being elected every day. And these nodes are then, the service that they offer is to perform a scalar multiplication. So what about the use cases for our human network? So as I introduced, one of is like create and generate human keys. So it's deriving cryptographic keys from human attributes. And another one, which is mainly used, is how to generate nullifiers for credentials. And this is super important and useful in the decentralized ID use cases, scenarios. And finally, we also have some use cases of provable encryption. It's where you can encrypt data using a public key, which is here is the public key of the network. And then with certain conditions, you can ask and require for the decryption. So now let's let's dive into the biometric authentication use case, which is what is the topic for today. So with biometric authentication, one main issue that we faced is what we call fuzziness, right? So what is fuzziness in this case is, okay, let me just explain what is the classical password authentication, right? So when you register to a service, to a platform, you are committing a password, right? And this password is being hashed, right? So it's being hashed with a cryptographic hash function, which is a function that will transform your password into some illegible string of characters, right? And this hash function, as one of the main characteristic of this function, is that it is deterministic, right? So that means that anytime you hash the same password, you will get the same hash value. But if you compute the hash of a password which is even really slightly different, you will get a totally different hash value, right? So this hash approach is quite straightforward to do equality test, right? So for authentication, it's quite easy. You ask once you commit your password, it computes the hash, and then if you want to authenticate and to like pretend to be the user, you just like provide the hash of the same password, and if the hashes matches, then yeah, you are authenticated. But what about biometric based and specifically the face recognition, right? So with face recognition, what you are committing is not a password, it is actually like a face, a picture of you, right? And so this picture of you, the face, is first encoded, right? Encoded into some, what we call an embedding, which is a vector of fixed size vector, right? And the thing is, even if you are committing two pictures of the same person, the embeddings will be different and could be like highly different, the two. So that's why it's not easy in that case to do equality test. So that is actually what is fuzziness and the issue that we face. So what are the other challenges that we need? So privacy, obviously, since we are here talking about biometrics, biometric authentication, we have to manipulate carefully all of the personal data, and privacy is one of the main requirements. And then it's correctness, right? Soundness, completeness, so you don't want any false positive or false negative. So here is our two steps protocol, right? So first of all, it's the enrollment. So enrollment is like when you are registering to a service. So you're providing your face, right? Picture of your face, which is encoded into an embedding, and you want this embedding to be encrypted, right? Because of the privacy requirements. And this embedding is then encrypted and then committed to the human network. Then you have the authentication phase. So it's like you pretend to be the user that first enroll. So you provide your face, right? Your picture of your face, which is by definition different as the previous one. And this encoding of your face, this embedding is then encrypted, and the two encrypted value are needed to be verified together by the network. Okay, so here are a couple of concepts that we are using here in our approach. So the embedding, right, obviously is how can we convert an image, a picture of you, of your face, into a vector of a fixed size. And then we have like, what are we doing with these embeddings, with these vectors, right? How can we, regarding this fuzziness, how can we apply computation on it? How can we check that they are actually belonging to the same person? And our approach goes with the Euclidean distance, which is like a really famous formula that allows you to compute the distance between two vectors. And finally, we have homomorphic encryption. So homomorphic encryption is maybe like the main idea of this approach. Homomorphic encryption is a type of encryption scheme where you are actually able to perform computation directly on the ciphertext, right? So that means that even if you manipulate ciphertext, which are like they are illegible data, you can still compute addition or multiplication on them, and then the decryption will be equivalent to the computation directly on the plain text. So there exist different kind of homomorphic encryption, partially, somewhat, fully. So partially means like you can only do one type of computation on that. So it could be addition or multiplication. Somewhat homomorphic encryption, that means that you can do, like, for example, an unlimited amount of addition, but only a couple of multiplication. And then you have the fully homomorphic encryption, FHE, which is kind of the holy grail of homomorphic encryption. That means that you can now perform an unlimited amount of addition and multiplication. So here you just need to know that FHE is quite costly, right? So even if like good progress have been made in the past couple of years, it's still quite costly in terms of computation, runtime, etc. So the lighter the scheme that you use, the better it is, right? So that's why partially homomorphic encryption are way more efficient if in your use case you only need to perform addition, let's say, or only multiplications. So here's a little of mathematics, but really simple. It's just like when you take the Euclidean distance formula and you just like develop it, you realize that when you take the square of it, the Euclidean distance between two vectors is actually only like 3 multiplications and 3 additions, right? So one trivial approach here for the biometric authentication is to encrypt the two vectors, the two embeddings, and to be able to perform the check on if, like, the authentication step, you will just need to perform 3 multiplication and 3 additions on the encrypted data. But what you can see also is that in case you don't just commit the encryption of the vector, but maybe the encryption of the square of the vector, or like -2 times the vector, you can reduce it and optimize the computation on the ciphertext up to 1 multiplication and 2 additions. But in either of these cases, you need both type of operations, right? You need both multiplication and addition, so that means that you need to use FHE or somewhat homomorphic encryption, which are quite costly encryption schemes. So here is now, we are now introducing like our human network into this approach, and we realize that what we can also be done is at the authentication phase, instead of just committing the encryption of its vector, it's like performing this scalar multiplication with the plain text of the vector and the encryption of the enrollment, right? So that means that by doing so, we will reduce it again even better to 2 additions. And since it's 2 additions, we are now using partially homomorphic encryption scheme, which needs only to be able to perform addition on ciphertext. And this is actually, there exists one, the ElGamal, the elliptic curves ElGamal encryption scheme, which is could be reduced and simplified to as the decryption to be a scalar multiplication. And that is actually what our human network is doing. Yeah, so that's actually how we are solving this issue here, is by using the human network as a third party, where users are encrypting their face and the embeddings to the human network public key. And this human network will be able, right, to perform the additions on it and then to decrypt the result to see the Euclidean distance between the two vectors, and then to be able to see, okay, and to state if the people is then authenticated or not. So just to recap a little bit our approach. So we just showed that for the Euclidean distance computation, for this biometric with face recognition, it could be reduced and simplified to only use the ElGamal public key encryption scheme. And this type of homomorphic encryption scheme needs to be able to perform computation on the ciphertext. You need to encrypt with the same public key, right? So that means that if different users would like to use this approach, they all need to encrypt with the same public key, such that the ciphertext could be computed together, right? So that's why we say, okay, so now we need to use the public key of the human network. Right, but then, okay, what about the privacy here? What about the human network privacy? Because the user will encrypt its data with the human network public key, which is okay, but then what about the human network? Concretely about the nodes and the operators, are they able to decrypt your personal data, your biometric data? And as I explained it before, the human network is a threshold network, meaning that if, so it's a T out of N network in the sense that, as I said, N nodes are sharing the secrets. And if you want to, like if an attacker would like to get your personal data, your biometrics, he will need to corrupt at least T nodes to be able to retrieve enough key shares to decrypt your specific biometrics, right? So in a way, we can say that this network is secured because, like, if we take a sufficiently high value for T, that it will need like too much power, too much effort for an attacker to corrupt all of the T nodes and then to retrieve the key shares, and then to get your biometric data. Yeah, that's okay. That's it for me. Thank you.
Any questions?
Thank you. Yeah, I think the work that you're doing here is really important for biosignal protection, and it's really fascinating. So thank you for the talk. I was wondering if you could elaborate on what it would look like if you were dealing with like a Bluetooth device that maybe had the algorithm to create the embedding. Would the encryption start on the device, or would the embedding need to get sent over to the human network and then get encrypted there?
Yeah, I mean, if so, your device will convert into embeddings, right? Mm-hmm. Yeah. So if your device has the ability and the computation power to encrypt, which is not that much of computation, yeah, it could be possible. Yeah,
okay,
it just needs it just needs the human network public key, and then the encryption scheme is quite straightforward. Yes.
Cool. And then I want to make sure I have one one more question, but you mentioned that the algorithm is based off of Euclidean distance, and because of that, you're able to make it like super efficient. Are there other algorithms that can be used also, or is it kind of a special property of Euclidean distance that it's able to be made this efficient?
So Euclidean distance approach is related to the way you are generating the embeddings, right? So it's depending on it's depending on the type of like with for example with face tech, when you are catching the face of the user, you can then choose the way you are generating the embeddings, and depending on that generation, that neural network computation, it will give you, okay, you can then do the matching based on Euclidean distance, and it gives you a threshold, like, okay, for this kind of embeddings computation, the Euclidean distance threshold will be, I don't know, like 20. So that means like if it's less than 20, that the people are actually the same, but if it's more, they are not the same. But yeah, I know that there exist different other ways to generate embeddings that are not using Euclidean distance, but other kind of metrics. But then, yeah, I mean, our approach like really match the Euclidean distance because of all the operations reduction that we made. But with other approach, maybe, I don't know, we have to check if it could work also.
Cool. Super cool. Thank you.
Hi, Louis. Thanks for the great talk. Could you explain a little bit about the trade-offs of selecting a T that's too high versus a T that's too low?
Yeah. So this the main idea of having a threshold network is to be able to combine security and also like accessibility of the service, right? So if you have n out of n, so that means that you need all of the nodes to be able like to do the computation to get the final result. In case you have one, which is like, let's say, offline or corrupted, or then it will fail the whole protocol and you cannot do anything, right? So if you take a small t value, that means that you can allow to have like a lot, like n minus t, a lot of nodes are like which are failing, right? So you can still be able to perform the service and to offer the service even if a large amount of nodes are not working well. Right? But if that t value is too low, then that means that any attacker can just like corrupt this t amount of nodes and be able to retrieve the secret, right? So it's kind of, as you say, like a trade-off between you want to offer high availability of service, so you don't want to have like a too large t, but also you need some certain amount of security, so you don't want to have a too low t. So usually, and what we do in practice is we take a t value which is more or less 2/3 of n value, right?
Yeah, that makes sense. How about, say, incentive mechanisms like slashing for optimizing performance or availability? Is that something that could be used to have a larger node participation count?
Yeah. So in our human network, in all of the protocols that are the key-resharing or the scalar multiplication, all of the multi-party computation protocols, we are able to identify in case one of the nodes is acting badly. So that's why at the moment we don't really consider slashing, because we can identify them and then we can just like blacklist them. But yeah, I mean, slashing is quite common in the AVS ecosystem. and especially with this risk-taking approach where the assets are being delegated multiple times, so that need some hard requirements on the good behavior of the nodes. So
So you could have like tens of thousands of nodes that help people biometrically authenticate and create keys, something like that, as opposed to like a more centralized set. And then have there been any conversations or thoughts on other types of biometrics, like say, like biosignals versus like maybe even like authentication related to say like mRNA sequences or anything like that? It's a pretty general approach, right?
Yeah, of course. I mean, for this presentation and for the first approach I took is face recognition, which I think is one of the most trivial approach of biometrics. But hopefully it could be applied to lots of different kind. And with AJ, I think we can maybe work together, to apply to the brain.
Yeah. And then how can I build if I wanted to get started?
You build. You mean to build on human network and this authentication? So just contact us. Contact Human Tech. We are starting to onboard projects to use human network. It's really straightforward, and we are providing good support for the devs to be able to query and to use human network.
Thank you.